Alright guys, so I had a request to make a little video about Le Chatelier's principle, and so here's the video. So I've broken down the principle into sort of a non-chemistry type sentence. If you mess with a system that is already at equilibrium, the system will try to counteract whatever you did. We can say this in a lot of different ways, but I think this is a good way to say it. So for this example, this explanation, I'm going to use this thermochemical equation that I've shown here. So this is a reaction that has N2 gas, H2 gas combining to form NH3 gas. I'm showing that it's an exothermic chemical reaction. And the first way that we can sort of mess with our system is by changing the concentration. So I think in class we've talked about adding in more reactants or taking away some products, or vice versa, adding in more products or taking away some reactants. And basically if you add in more reactants, that's going to shift the equilibrium to the right. It's going to push, for the formation of more products. If I take those products away, that's again going to shift the equilibrium to the right. It's going to reform some of those products. If we mess with the system will try to counteract what we do. So I think with the concentration things, we're doing okay. I do want to point out, when I change concentrations, Kc will stay the same. So if I don't change, the only thing I change is the concentrations, the Kc value for this equilibrium, that will stay the same, that will stay constant. And we can imagine, at that instant that we've added more reactants or have taken away some products, then we're sort of doing that QC-Kc comparison thing. So if I take out the products, for instance, and I want to calculate QC now that I've taken those products out, that QC value will be too small. That means I'll need to reform more of those products. The second way that I can mess with the system is by changing the pressure, and I'm talking about the external pressure here. So the external pressure, that's going to affect this equilibrium really based off of the number of moles of gas that are present in my system. The idea here is that if I started with just reactants, so sort of just starting with just reactants, I've got 4 moles of gas total. If I go to completely products, if I said, okay, I'm going to run this reaction completely to the right, I'm going to end up with 2 moles of gas. So one way to think about it is, if I start here, and let's say that I start here and I have a 2 atmosphere total pressure, and I go here and I go completely to products, now I will only have a 1 atmosphere total pressure. My pressure is going to decrease by half simply because I've got more moles of gas on the left-hand side, less moles of gas on the right-hand side. So if I change the external pressure, if I put more pressure, I squeeze things together, well, the equilibrium will try to counteract whatever I've done. So if I'm putting more pressure on the system will shift in a way to alleviate some of that pressure. By moving more to the right, this system can alleviate that pressure because, again, I've got more moles of gas on the left, less moles of gas on the right. So putting pressure on this system is going to shift the equilibrium towards the side that has less moles of gas. Now, changing temperature, again, it's going to change the Kc value. And the delta T thing, the change in temperature here, that's going to be related to if it's an exothermic or endothermic reaction. So in this case, we've got an exothermic reaction. So an exothermic reaction I really think of as writing plus heat on the right-hand side. We're evolving heat, we're generating heat. So that's how I'm gonna put my plus heat on the right-hand side. Now, if I raise the temperature of this reaction, I say we're going to do this reaction at 45 degrees Celsius as opposed to 25 degrees Celsius. Well, the way I think about it is essentially I'm adding in heat. I'm adding in more of this product. Well, that should shift the reaction to the left, and that's exactly what we would observe. So that shifting of the reaction to the left, that's going to change the Kc value. Now, bear in mind, this is for this example that I'm talking about, this is for this chemical reaction, which is an exothermic reaction that has more moles of gas as reactants and less moles of gas as products. So you can't just memorize what I've just said, because if I give you an endothermic reaction, well, all this is going to change. The logical progression of, if I change the pressure, how will the equilibrium react? If I change the temperature, how will the equilibrium react? Based off of what reaction you are actually looking at, that's really the key here. So if there's any other things that you're confused about with this, let me know, and I'll try to clear those up. in the comment section, or I can post a new video. But hopefully that sorts things out for you guys.